Let's see how we can simplify the process that we saw in the previous video by using the idea of electrical impedances. So again, as I mentioned at the end of the previous video, what we're going to do is we're going to convert the individual circuit elements to our frequency domain first before we write any equations or do any analysis. And so what we're going to see in the next video is that using these impedances, we can greatly simplify the process. So in general, we can define our impedances using our Ohm's law for phasors. So general impedance equation is given by impedance is Z of S is equal to V of S divided by I of S. So notice these are all functions of S, so we're in the frequency domain. And so of course we could rearrange this and we could say that our V of S is equal to I of S times Z of S. So in order to find our impedances of each element, our capacitor and inductor and resistor, let's take the Laplace transform of each of those IV equations. So let's take our Laplace transform of our IV, so IV stands for current voltage equations. So let's start by looking at our capacitor. So for our capacitor, again, this information can be found in table 2.3. And so for our capacitor, we see we have V of t is equal to 1 over c times the integral of I of tau d tau. So where tau is just a dummy variable. So if we do Laplace transform and we use our Laplace transform properties, and what I'm going to do is, in this case, because we have an integral, I'm going to use the integral property. We see that the Laplace transform of this is V of S equals 1 over c times I of S divided by S. Okay, so let's do a similar thing for our inductor and resistor, and then we'll come back and we'll sort of comment on what the impedance is for each element. So inductor, for our inductor, as we saw in the previous video, our voltage for the inductor is equal to L di dt. So if we take the Laplace transform of that, we use our differentiation property. So we can say V of S is equal to L times S I of S. And so again, note we're assuming zero initial conditions, so the table 2.3 explicitly says zero initial conditions are assumed. So then finally for our resistor, we just have good old Ohm's law. So we can say V of t is equal to R times I of t, so no derivatives or integrals here. So we're just using our linearity property to say that V of S is equal to R times I of S. Okay, so now what we want to do is we want to compare these three equations to this sort of general form. So of course we can see we have Vs and I of S in each equation, and whatever is left over is going to be this Z of S. So for example, in our capacitor equation, we can see that that's going to be 1 divided by S times C. For our inductor equation, it's this L times S. And for our resistor equation, it's simply R. So in summary then, what we can say for our impedances, for our common elements, we have Z sub C is equal to 1 over S times C, where C is our capacitance. Z of L is equal to S times L, where L is our inductance. And Z of R, so our resistor impedance in the frequency domain, so that's why I have the parentheses function of S, is simply just equal to the resistance R. So these would be our three key impedances for our basic passive components. What we're going to do in the next video is we're going to take a look at that circuit again that we looked at in the previous video and see just how much using these impedances can simplify the process. Another useful thing to be aware of, which we're going to talk about when we get to our generalized equation, is admittance. And so admittance is just the inverse of impedance. So typically admittance is going to be represented with y. So if we're in the frequency domain, I'll have capital Y as a function of s. And as I said, that's just defined as the inverse of impedance, so 1 over z of s. And so of course that's just going to be our I of s over v of s. And we'll see how that comes into play as we look at our sort of general equations in a couple videos.